Let us now study the properties of determinants. So property number 1. The value of the determinant remains the same if the rows and columns are interchanged. The value of the determinant remains the same if the rows and columns are interchanged. Let us verify this first with an example. So I will consider the determinant 1, 2, 3, 4. So what is the value of the determinant? 4 minus 6, that is minus 2. Now I will interchange the rows and columns. 1, 2 was the first row. Now I will make it the first column. 3, 4 was the second row. I will write it as the second column. So I have interchanged rows and columns. First row has become first column. Second row has become second column. Okay. So now what is the determinant of this? So 4 minus 6. Answer is minus 2. It is one and the same. So you interchange the rows and columns, the determinant remains the same. But an example is not a proof. You have to prove this property in general. So we will prove this property in general for a 3 cross 3 matrix, taking the general elements, not numbers. Okay. So example does not become the proof. You have to prove it more generally. Let us see the proof now. Let delta 1 be the determinant of this, that is A1, A2, A3, B1, B2, B3, C1, C2, C3. Okay. So we have to prove it generally. So we will be considering 3 cross 3 determinant, and we will be proving it by taking general elements like A1, A2, A3, B1, B2, B3, C1, C2, C3. Now if you expand this determinant delta 1, what do you get? Expand this about the first row, plus minus plus. So A1 into, delete this, so what will remain? B2 C3 minus C2 B3. Next we need to write minus A2 into, delete the row and column in which A2 is present. So delete this and delete the first row. So what will remain? B1, B3, C1, C3. So it is B1, C3 minus C1, B3. I am writing this directly. I have avoided the step of writing the determinant. Okay. So deleted this, this was remaining. So I directly calculated the determinant and I wrote here. So minus A2, delete this, B1, B3, C1, C3 will remain. So when you multiply it becomes B1, C3 minus C1, B3. Okay. We will be avoiding that step. So plus A3 into, delete the row and this column. So what will remain? B1, B2, C1, C2. So how to find out the determinant? B1, C2 minus C1, B2. B1, C2 minus C1, B2. Now I will open up the brackets and I will simplify this. When I write, I will take care. I will write it in the form A, B, C only, so that checking becomes easy for us. Okay. So A1, B2, C3, A, B, C, they are in order, minus A1, B3, C2. So A, B, C, I am writing it in order, minus A2, B1, C3, minus into minus, plus A2, B3, C1 plus A3 B1 C2 minus A3 B2 C1. So keep it aside. So this is delta 1, that is the determinant of this matrix. Now let delta 2 be the determinant obtained by interchanging the rows and columns. Okay, let delta 2 be the determinant obtained by interchanging the rows and columns. So the first row here becomes the first column. So A1, A2, A3, B1, B2, B3, C1, C2, C3. Okay. Now let us expand this delta 2 about the first row. So plus minus plus. So plus A1 into, I will write directly. So delete this. So only this much will remain. So it is B2 C3 minus B3 C2. Okay. Then we have minus B1 into, delete the row and column in which it is present. So A2 C2, A3 C3 will remain. So when you multiply A2 C3 minus A3 C2 plus C1 into, delete the first row and the third column. So A2 B3 minus A3 B2. Now simplify. A1 B2 C3 minus A1 B3 C2 minus, write it in the order ABC, it becomes easy to verify. So A2 B1 C3 minus into minus plus A3 B1 C2 plus A2 B3 C1 minus A3 B2 C1. Check whether delta 1 is same as delta 2. See the suffixes 1, 2, 3, that is A1 B2 C3, we have it here. Next we have minus A1 B3 C2, that is also there, minus A2 B1 C3, that is there, plus A3 B1 C2, A3 B1 C2, it is there, A2 B3 C1, A2 B3 C1 and minus A3 B2 C1, that is also there. So all the terms we have checked, both are equal. So delta 1 is equal to delta 2. Therefore delta 1 is equal to delta 2. So if you interchange the rows and columns and find out the determinant, the determinants will be the same. Property 2, determinant changes its sign when any two of its rows or columns are interchanged. So determinant changes its sign. If it is plus, it becomes minus. If it is minus, it becomes plus. But when? When any two of its rows or columns are interchanged. Let us first check it with an example whether the property is true or not. Let us just check. So let me consider this example. So let us expand the determinant. So plus minus plus. So plus 1 into, delete this. So 1 into 3, 3 minus 2 into minus 1 is minus 2, this becomes plus 2. Minus 1 into, so this was plus 1, you have to write it as minus 1. Delete the second column and the first row, you will get 0 into 3, that is 0, minus of minus 1, that becomes plus 1. Then we have plus 2 into, delete the first row and the third column, 0 into 2 is 0, minus 1. So 0 minus 1. Simplify, 5 minus 1 and there it is minus 2. So 5 minus 3, that is 2. Now what we will do is, we will interchange any two rows. Okay, interchange any two rows. So let me interchange the first and the second row. So first row I will write it as the second row and the second row I will write it as the first row. So I have interchanged the first two rows. Let us see what will happen to the determinant. So first it is 0 into anything is 0, so you need not check. Here it is, change the sign, it is plus 1, write it as minus 1. Delete this, 1 into 3 is 3 minus 2. As it is, you should write minus 1 into, delete the first row, third column, so 1 into 2 is 2, 2 minus 1. So what do you get? This is 0, then you have 3 minus 2 is 1, so this is minus 1, and here you have 2 minus 1 is 1, 1 into minus 1 is minus 1, minus 1 is minus 2. Observe here, the value of this determinant was plus 2, but when you interchanged two rows, the value became minus 2. So that is what this property is saying. Determinant changes its sign when any two of its rows or columns are interchanged. I took an example by interchanging its rows. You can also interchange the columns and verify the result. Okay, this is just a verification but not the proof. We need to prove it more generally. Let us prove this now. Proof. Let delta 1 be the determinant A1, A2, A3, B1, B2, B3, C1, C2, C3. So when you expand this, you will get delta 1 is equal to A1 into, same like before, B2 C3 minus C2 B3. Then you have to change the sign, that is minus A2 into, delete this, you will get B1 C3 minus C1 B3. Keep the sign as it is. So A3 into B1 C2 minus C1 B2. Okay. Let us simplify this as before. A1 B2 C3 minus A1 B3 C2 minus A2 B1 C3 plus A2 B3 C1 plus A3 B1 C2 minus A3 B2 C1. Let us keep this as it is. Let delta 2 be the determinant obtained from delta 1 by interchanging the first two rows. So delta 2 be the determinant obtained from delta 1 by interchanging the first two rows. We need to interchange the first two rows now. So delta 2 is equal to, second row I will write it as the first row. So B1, B2, B3, A1, A2, A3, and the third row as it is, C1, C2, C3. Okay. Now let us expand this. Delta 2 is equal to plus minus plus, so it is B1 into, delete this, so A2 C3 minus C2 A3. Next change the sign, so minus B2 into A1 C3 minus C1 A3 plus B3 into A1 C2 minus C1 A2. Now simplify this. Let us follow the order ABC when we are writing so that it becomes easy to check. So A2 B1 C3 minus A3 B1 C2 minus A1 B2 C3 minus into minus plus A3 B2 C1 plus A1 B3 C2 minus A2 B3 C1. Definitely these two are not equal. We wanted change in sign. So if you observe now, take out the minus sign and see what you get. If you take out the minus sign, you will get, let us search for this, A1 B2 C3. A1 B2 C3. The sign is minus. So I have taken this minus sign out. So what will come here? Plus. The minus becomes plus. A1 B2 C3 because I am taking out the minus sign. So this term is done. Next A1 B3 C2. So 1 3 2. It is here. Here it is minus. Here it is plus. Since I have taken the minus sign out, this plus becomes now minus A1 B3 C2. So this term is done. Next 2 1 3, if you check, 2 1 3 is here. Here it is minus. Here it is plus. So this becomes minus now because sign is outside. A2 B1 C3. So this is also over. 2 3 1. The last one, change the sign, plus A2 B3 C1. 3 1 2. This is minus. So it becomes plus A3 B1 C2. So this is done. Then 3 2 1. 3 2 1 is here. Write it as minus A3 B2 C1. So if you take out the minus sign, the signs of all these terms will change. This was plus, it has become minus. This was minus, it has become plus. So similarly for all the terms, because you have taken out the minus 1 here. Now if you observe minus, what is this? Whatever is inside the bracket. Whatever is inside the bracket is nothing but delta 1. So if you interchange any two rows or any two columns, the sign of the determinant will change. So you have the indication here saying it is minus, which means the sign will change. So delta 2 is nothing but minus delta 1. Property 3, the value of determinant is 0 if any two of its rows or columns are identical. What do you mean by identical? Same. If any two of its rows or columns, if they are same, then the value of the determinant is 0. So let us just check. I will consider the determinant. Say 1 1 1, 1 1 1. Two rows are identical. Then I will consider 2 1 3. So these two rows are identical. They are the same. So I should get the determinant 0. Let us check whether we will get. So 1 into 3 minus 1. Change the sign, minus 1 into, delete this, so 1 into 3 is 3, minus 2 into 1 is 2, plus 1 into, delete this, so 1 minus 2. So 3 minus 1 is 2, minus 3 minus 2 is 1, so you will get 1 itself, 1 minus 2 is minus 1. So this becomes minus 1. So this is nothing but 2 minus 2, that's equal to 0. So if any two rows or columns, the property holds even for columns. So here in the example I have taken two rows identical. So we are getting the determinant 0. So we have verified the property. Now let us prove it. Proof. So let delta be equal to, because there is only one determinant here, we need to consider two rows identical. So let me consider A1, A2, A3. So first two rows I have to take it same. So I have to take A1, A2, A3, A1, A2, A3. That is what the property is saying. Choose any two rows which are identical. So I have chosen the first two to be identical. Then I can take B1, B2, B3. Okay. Now let me expand this determinant delta equal to. So A1 into, delete this, so A2 B3 minus B2 A3, change the sign, minus A2 into, delete this, so A1 B3 minus B1 A3 plus A3 into, so A1 B2 minus B1 A2. Let us simplify this. A1 A2 B3 minus A1 A3 B2 minus A2 A1 B3 plus A2 A3 B1 plus A3 A1 B2 minus A3 A2 B1. Now let us see if we can simplify this further. A1 A2 B3. So A1 A2 B3, here the sign is plus, here the sign is minus, so this will get cancelled. A1 A3 B2, A1 A3 B2, this is plus, this is minus, A2 A3 B1, A2 A3 B1 plus and minus. So everything will get cancelled. So what remains is nothing but 0. So the value of the determinant is 0 if any two of its rows or columns are identical. Property 4, if in a determinant the elements of any row or column are multiplied by the same scalar, say k, then the value of the new determinant is k times the given determinant. Well, I'll explain you this property with an example first. Let me consider the determinant 1, 2, 3, 4. So 4 minus 6, which is minus 2. Now what I will do is, I will multiply the first row with the number 3. So I am considering k equal to 3 and I will multiply this scalar to the first row. So 3 into 1 is 3, 3 into 2 is 6. Second row as it is, I am multiplying this only to the first row. So the scalar, if in a determinant the elements of any row or column are multiplied by the same scalar. So any row is multiplied by the same scalar. So I am multiplying the first row with the same scalar 3. Now check what happens to the determinant. 3 4s are 12, 6 3s are 18. So the answer is minus 6. So what has happened to the new determinant? The new determinant obtained is scalar times the old determinant. Is it not? 3 into minus 2 gives you minus 6. So new determinant is nothing but scalar times the old determinant, that is k times the old determinant delta 1. Okay, if you consider delta 1 as the old determinant, this scalar as k, then the new determinant will be equal to k times delta 1. That is scalar times the old determinant. So this is what the property is saying. So we have verified it. So let us prove it. Proof. Let delta 1 be equal to A1, A2, A3, B1, B2, B3, C1, C2, C3. So if you expand the determinant delta 1, what do you get? A1 into, we have done this many times, B2 C3 minus C2 B3 minus A2 into B1 C3 minus C1 B3 plus A3 into B1 C2 minus C1 B2. Let me keep this as it is. I will not simplify. Let us keep it as it is. Now, let delta 2 be the determinant, obtained from delta 1 by by multiplying the scalar k to the first row. Let delta 2 be the determinant obtained from delta 1 by multiplying the scalar k to the first row. So, how will be delta 2 then? It will be Ka1, Ka2, Ka3, remaining elements as it is. Yes, now let us expand about the first row plus minus plus. So, it is Ka1 into, delete this, so B2C3 minus C2B3 minus Ka2 into B1C3 minus C1B3 plus Ka3 into B1C2 minus C1B2. Okay. Now, if you observe, k is common in all the terms. So, let us bring that k out. So, if you bring the k out, what will remain? A1 into B2C3 minus C2B3 minus A2 into B1C3 minus C1B3 plus A3 into B1C2 minus C1B2. So, that is equal to k into, what is this? Whatever is inside the bracket, compare this with this, it is nothing but delta 1. So, delta 1, here it is delta 2. So, the new determinant that we obtained is scalar times the old determinant. Please note that property 4 is saying if in a determinant, say in this, if you observe in the first row 2 is a common factor there, okay. You can write 6 as 2 into 3, this as 2 into 4, this as 2 into 5. So, the number 2 is common in the first row. So, you can bring that outside the determinant, that is what property 4 is saying. Bring the 2 out from the first row, then what remains is 3, 4 and 5. Rest is as it is. So, this is what the property 4 is saying. In case there is any common number or common factor in any of its row or column, you can bring it outside, okay. So, remember this will be used in solving the problem. So, whenever you see a common number in any row or column, you can bring it outside. Property 5. If each element of any row or column of a determinant is the sum of two terms, then the determinant can be expressed as the sum of two determinants. What does this mean now? Let me explain you with an example. I will consider say 1 plus 2 and 2 plus 2, 3 and 1, okay. So, if each element of any row of a determinant is the sum of two terms. Now, in the first row, I have considered sum of two terms. Actually, this is nothing but 3, this is nothing but 4. But I have written it like this in order to explain this property. So, 1 plus 2 and 2 plus 2. Now, let us simplify this. Let us expand the determinant. This is 3. 3 into 1 is 3 minus, this is 4 and this is 3. 4 3s are 12. So, 3 minus 12 is nothing but minus 9. Let me keep this aside. Now, I will write the same thing as 1 3 2 1 plus 2 3 2 1. Observe, second row is as it is 3 1 3 1, but what has happened to the first row? I have split it. So, first write 1 2, then this 2 and this 2. Okay. Now expand the determinant and add. So what will happen here? 1 into 1 is 1, 3 2s are 6, so 1 minus 6 plus 2 1s are 2 minus 6. So 2 plus 1 is 3, 3 minus 12 you will get, answer is minus 9. So observe here, if each element of any row of a determinant is the sum of two terms, then the determinant can be expressed as the sum of two determinants. Sum of two determinants. Okay. So if it is like this, in case the first row is a sum of two numbers, you can express it like this also. So the determinant will not change, it will remain the same. Let us prove this property. So proof, let delta 1 be equal to a1 plus x, a2 plus y, a3 plus z. Then b1, b2, b3, c1, c2, c3. Okay, so I am expressing the first row as the sum of two terms. So if I expand this determinant, what will happen? So a1 plus x into, delete this, delete the first row, b2 c3 minus c2 b3, then change the sign. So minus a2 plus y, put the bracket, delete this, so b1 c3 minus c1 b3 plus a3 plus z into b1 c2 minus c1 b2. Let me simplify this. Multiply a1 with the whole thing, then x with the whole thing. So here a2 with the whole thing, y with whole thing. So we will multiply like that. So I will write a1 into b2 c3 minus c2 b3. I will keep this multiplying x as it is pending. I will multiply the a2. So minus a2 into this full thing. So b1 c3 minus c1 b3. Then multiply the a3. a3 into b1 c2 minus c1 b2. Now multiply x, y, z. Multiply this x with this full thing. b2 c3 minus c2 b3. Then minus y into b1 c3 minus c1 b3 plus z into b1 c2 minus c1 b2. Observe this. I will write this as determinant a1, a2, a3, b1, b2, b3, c1, c2, c3 plus determinant x, y, z, b1, b2, b3, c1, c2, c3. Check whether I can write like this. Let us check with the first thing. a1 into b2 c3 minus c2 b3. So a1 into b2 c3 minus c2 b3 minus a2 b1 c3 minus c1 b3 plus a3 into b1 c2 minus c1 b2. So this expansion is nothing but this determinant itself. Similarly, in the place of a1, a2, a3, it is just x, y and z, remaining everything is same. So second part is nothing but this determinant. So we have written delta 1. Delta 1 was nothing but this determinant. So this determinant can be written as the first term here plus the second term. So if at all any row is a sum of two terms, we can express it as sum of two determinants. This is what the property is saying. So if any if each element of any row of a determinant is the sum of two terms, then the determinant itself can be expressed as sum of two determinants. Okay. So, this is property 5. Property 6. If each element of a row or column is multiplied by a scalar and added to the corresponding elements of any other row or column, then the value of the determinant is unaltered. Let me consider an example. Consider this determinant 1, 2, 1, 3, 1, 4, 1, 0, 2. Let me expand this. 1 into 2 minus 0 minus 2 into 6 minus 4 plus 1 into 0 minus 1. So, you will have 2, 6 minus 4 is 2, so you have minus 4 and it is minus 1. So, the answer is, this is minus 4 minus 1 is minus 5, 2 minus 5 is minus 3. You have the value of this determinant as minus 3. Now, what is this property saying? If each element of a row is multiplied by a scalar and added to the corresponding elements of any other row or column, then the value of the determinant is unaltered. Now, I will keep the third row and the second row as it is. Let me carry out the operation as told by property 6. Multiply a scalar to each element of any row. So, I will multiply 2. So, scalar I am considering 2. Multiply the scalar 2 to this second row and add it to the elements of the first row. So, what is 2 into 3? 6. What is 6 plus 1? 7. 2 into 1 is 2. 2 plus 2? 4. 2 into 4 is 8. 8 plus 1 is 9. Okay. So, multiply the scalar to any row and add it to the corresponding elements of any other row. So, when I say multiply scalar 2, you do not have to multiply to the second row. That should be done mentally. Multiply in your mind and add it to the first row. So, operation is multiply the scalar to any row and add it to the corresponding elements of any other row. So, let us now see what is the determinant value of this. So, 7 into 2 minus 0 minus 4 into 6 minus 4 plus 9 into 0 minus 1. So, this is 14. 6 minus 4 is 2. So, this becomes minus 8 and here you have minus 9. So, minus 8 minus 9 is minus 17. Minus 17 plus 14 is minus 3. See the beauty of this property. So, determinant remains the same. Determinant is unaltered. So, determinant is same. What was the operation? Multiply a scalar to any row and add those numbers to the corresponding elements of any other row. So, the multiplication that is carried out should be in your brain. No multiplying literally to the second row here, okay. So, multiply in your mind and then add it, okay. That is what this property is saying, that if you do such an operation, the determinant will not change. So, let us prove this property more generally. Proof: let delta equal to A1, A2, A3, B1, B2, B3, C1, C2, C3. Okay. Let this be as it is. You need not even expand this. Keep it as it is. Now, let delta 1 be equal to, this is delta, I am taking delta 1 as, what I am doing is, I am multiplying a scalar k to the second row and I am adding it to the first row. So, second row and third row as it is, whereas for the first row, I am adding k times the second row. So, A1 plus KB1, A2 plus KB2, A3 plus KB3. So, first I multiplied the constant or the scalar k to the elements of the second row. So, KB1, KB2, KB3. That was done in my mind. Then I added those numbers to the corresponding elements of the first row. First row had only A1, A2 and A3. So, I am adding now KB1, KB2, KB3 to the corresponding elements. So, that is what I have done here. Okay. So, now if you remember property 5, what does property 5 say? If any row is a sum of two terms, then you can write the determinant as sum of the two determinants. So, I will use the property 5 for the next step. So, it is A1, A2, A3, B1, B2, B3, C1, C2, C3 plus KB1, KB2, KB3, B1, B2, B3, C1, C2, C3. So, this is by property 5. Property 5. Look at this, A1, A2, A3, B1, B2, B3, C1, C2, C3. That is nothing but your delta, determinant delta. So, delta plus, delta 1 is equal to delta plus. What is your property 4 saying? Property 4 says, if there is a common factor in a row, see here, k is a common factor in the first row. You can bring it outside the determinant. So, I am bringing the k outside and writing what is remaining. What will remain? B1, B2, B3, B1, B2, B3, C1, C2, C3. So, this is by property 4. Anything common in a row or column can be pulled outside. Okay, so k is written outside. So, delta plus k into. What is your property 3 telling? Property 3 tells, if any two rows or columns are identical, then their determinant is 0. So, if you observe B1, B2, B3, B1, B2, B3, the first two rows are identical. Therefore, the determinant of this is 0 by property 3. So, k into 0 is 0. So, delta 1 is equal to delta itself. So, the determinant is unaltered. The determinant is the same. Please note the important point under property 6. If the scalar that you multiply is 1 and minus 1, let us see what happens. Okay. So, let me consider more generally A1, A2, A3, B1, B2, B3 and C1, C2, C3. So, this determinant is the same as we did just now, KB1, A1 plus KB2, A2 plus KB2, A3 plus KB3. So, B1, B2, B3, C1, C2, C3. So, this is what property 6 is saying. It is saying that these two determinants are same. Now, what if k is 1? What if k is equal to 1? Then we get like this, A1 plus B1, A2 plus B2, A3 plus B3. So, what we have done here, now compare the two determinants. We have simply added the first two rows and written it in the place of first row. So, first row is replaced by first row plus second row, A1 plus B1, A2 plus B2, A3 plus B3. We have done that addition and we have replaced it in the first row. So, even when we do this, the determinant remains the same. So, the operation which is valid is the first row, the new row is replaced with R1 plus R2. For the first row, you are adding the second row, the elements of the second row. So R1 is replaced by R1 plus R2. When you do this operation, the determinant remains the same. So if k is 1, then this operation is valid, and under this operation, the determinant remains the same. What if k is minus 1? So here there was k, now put minus 1. So what we have done is, looks like we have subtracted the second row from the first. A1 minus B1, A2 minus B2, A3 minus B3. So the operation R1 replaced by R1 minus R2 is a valid operation under which the determinant remains the same. Okay, determinant will not change if you do these two operations. Remember this because it is needed when we solve the problems. Okay, so property 6 is very, very important in solving the problems. Property 7, if all the elements in a row or column of a determinant are zeros, then the value of the determinant is 0. So let me take an example. Let me consider the determinant 1, 2, 3, then entire row 0. That is what is given in the property. If all the elements in a row of a determinant are zeros. So I am considering all the elements in the second row to be 0. So then I will consider 3, 4, 5. So let me expand this. What will happen? 1 into 0 minus 0, that is 0, minus 2 into 0 minus 0, that is 0, plus 3 into again 0 minus 0, that is 0. So 0 into anything is 0, you add any number of zeros, answer is 0. So if any row or column is completely filled with zeros, then the value of the determinant is also 0. Let us now prove this. Proof. Let delta equal to, let me consider A1, A2, A3, 0, 0, 0, C1, C2, C3. Okay, now expand the determinant about the first row. A1 into 0 minus 0, change the sign, minus A2 into 0 minus 0 plus A3 into, delete this, so 0 minus 0 once again. So what do you get? A1 into 0 minus A2 into 0 plus A3 into 0. So answer is 0. So if any row or column of a determinant is 0, then the determinant will be 0. This is property number 7. Property 8, if all the elements on any one side or both sides of the principal diagonal are zeros, then the value of the determinant is equal to the product of the elements in the principal diagonal. So let me explain you this with an example. Consider the determinant 4, 0, 0, 5, 2, 0, 7, 3, minus 2. If all the elements on any one side or both sides of principal diagonal, so this is the principal diagonal, I have considered the elements on one side, that is the upper side. All the elements in the upper side are zeros here. So then what will be the value of the determinant? Value of the determinant will be equal to product of the elements in the principal diagonal. So who are the elements? These are the elements of the principal diagonal. So the answer, they are saying that according to the property, answer should be 4 into 2 into minus 2. So let us verify. Let us expand the determinant first. 4 into, delete this. So 2 into minus 2 is minus 4 minus 0. Then minus 0 into anything is 0 plus 0 into anything is 0. So what will be the answer? Minus 16. This minus 16 is nothing but 4 into 2 into minus 2. So 4 2s are 8, 8 2s are 16, so minus 16. So the answer that you get when all the elements on any one side or both the sides are all zeros, then the answer will be the product of the principal diagonal. Let me take one more example with zeros on both the sides. Say 4 0 0. This is also 0, 1 0 0. So this is the principal diagonal. Elements on both the sides are all zeros. So expand this. 4 into 2 minus 0. Then you have 0 and 0. So no use calculating. So 4 2s are 8 is the answer. 8 is nothing but 4 into 2 into 1. So if all the elements on any one side or both sides of the principal diagonal are zeros, then the value of the determinant is equal to the product of the elements in the principal diagonal. Let us now prove this in general. Proof: let delta equal to A1, A2, A3, 0, B2, B3, 0, 0, C3. So the lower part is 0 now. So expand the determinant. A1 into B2, C3 minus 0 minus A2 into 0 minus 0 is 0 plus A3 into 0 minus 0 is 0. So what remains? A1, B2, C3. So A1, B2, C3 is nothing but the elements of the principal diagonal. So if all the elements in the lower side or the upper side are zeros, then the determinant will be equal to product of the elements in the principal diagonal.